Okay, okay, good evening, everyone. I continue from where I stopped from the first recording. This is Mr. Johnny on Engineering Mathematics, MCH 103. We are going to continue from sorts, having looked at set and inequality. Briefly, let me run through the other topics we're supposed to have on this course. Surge indices after seeing set inequality, logarithmic and exponential function, quadratic equation, equations of lines and circles, arithmetic projection and geometric projections, mapping, permutation and combination. We also see in this course polynomial, trigonometry, differential calculus, integration like hospital rule and Taylor and Maclaurin's series, Taylor and Maclaurin series. So we move straight to sorts. What are sorts? Sorts are simply irrational numbers, right? Numbers that do not have integers as their square roots. All right. We see some examples right on your screen. We are still going to be patching up with the notations as this platform do not allow upload of some of these mathematical notations. So some examples of surds, we have root 44, 3 root 808, 83, okay, root 3, those are surds value, root 3 root 2 to okay, sorry. Yeah, root 66, root 223, and so on. Root 20. They do not have proper roots. They do not have proper roots. So they are examples of surds. Expressions that are not surds can be root 4. So what you have on your screen instead of roots, yeah, root 4, root 9, all right, root 25. These are examples of expressions that are not surds because these expressions have integers of their square roots. Okay, so having seen that, we see types of surds. Types of surds, we have the pure surds, the mixed surds, all right, compound surds, compound surds. So the pure surds, a surd having only a single irrational number is called a pure surd. For instance, you have root 7 is a pure surd, 4 root 11, okay, root 3 is a pure surd. We have mixed surd, here we have mixture of integers and a surd expression, right? For instance, 4 root 3, right? 4 root 3, 8 root 5, these are mixed surds, compound surds. Here we have either addition or subtraction of 2 or more surds. These are compound surds. You see examples on your screen. 4 plus root 3. We also have 5 root 5 plus root 2. All right. Other examples are there. Root a plus b, root a plus b, and so on. All right. Now, the rules of surds. The rules of surds. Sorry. Now we'll consider some rules here. First and foremost, right on your screen, surds cannot be added. All right, surds cannot be added when they are not like terms. All right, just as you have in your basic algebra. All right, so you have, for instance, root a plus root b. Okay, just as we have for root A plus root B, okay, are not like terms, okay, they cannot be added. They cannot be added, all right? Root X and root Y cannot be added. Similarly, for subtraction, root A minus root B cannot be added or cannot be subtracted, okay? So we see that, but you can multiply, you can actually add up root A plus root B, all right, to give 2 root A. You can also subtract root 2 like sorts, all right, and simplify them further. Okay, so sorts can be multiplied. Sorts can be multiplied. For instance, you have root A times root B to give root AB, root AB. All right, sorts can also be divided. You have root A divided by root B to give root A over B, root A over B, root A over B. Okay, we've seen that, we've seen that. So there is the task for you right on the screen, just for it to simplify or find the solution of the following. You have 2 root 5 plus root 3 plus root 2 plus root 5 plus 2 root 3. Okay, if you can do that, okay, apply basic algebra as you've got the fundamental knowledge of that. Now, other operations in sorts, we have simplification of sorts. You've seen addition and subtraction. You can simplify sorts by adding and subtracting. Like terms, okay, like sorts, for like sorts. We can multiply and divide or do divisions on sort expression, okay? Then we also have expressing sorts in a simple form, expressing sorts in a simple form. That's simplification of sorts. So for instance, you have on the screen shown to you, you have root 50. You simplify further root 50 into prime factors, you have root 5 times 5 times 2. Okay, so we take root 25 times 2, that gives us 5 root 2, 5 root 2. Okay, so that helps 5 root 2 as final answer. So 5 root 2 as final answer to simplify root 50, root 50. The answer you have where you have 52 is actually 5 root 2, 5 root 2. All right, now we see some more examples, okay, to simplify. We have, let us use the above steps to perform the following calculation. You have root 18 plus root 50, 18 root 50, then plus 50 in attempt that, all right, back in your library period. All right, we also have examples. Convert 80 root 80 into mixed or simplify um, to a simpler expression. So root 80, you are going to split 80 into product of prime factors, right, to give you 2 times 2 times 2 times 2 times 5. Okay, so we take 2 times 2, which is 4, all right, or the square root of 16, which is 4. So you have 4 and root 5. 4 root 5. 4 root 5. Okay. Expressing root 80 in mixed sword, you have 4 root 5. We also have find the product of 4 root 3 and root 2 root 5. Right? You're simply multiplying 4 root 3 and 2 root 5 to give you 8 root 15. 8 root 15. All right? You see more examples on your screen. You see more examples on your screen. Kindly take notes and attempt on your own. Yes, expansion, surd expressions or binomial expressions in surds can be expanded. You have 4 plus 3 root 2. The square of 4 plus 3 root 2, simply for you to expand, just like you could do in the usual algebra, right? Further examples are shown to you on the screen. Further examples are shown to you on the screen on products of sorts. Okay, expansion, where you have to open up brackets to simplify products of sorts. Okay, find examples on your screen. Find examples on your screen. All right. So we also see other operations in sort, rationalization of sorts. All right. We also see conjugate of sorts. Conjugate of sorts. If a sort is given by the expression 3 root 5 minus 2 root 6, we say that the conjugate of the sort is simply to change the sign, to the opposite sign, right? 3 root 5, it becomes 3 root 5 plus 2 root 6. 3 root 5 plus 2 root 6. Okay. We also see the operation of rationalization of sorts, whereby for a fractional sort, rationalization comes in when you have a sort as the denominator of a fractional sort. Okay, where you have a sort expression as the denominator. So what do? You multiply both sides or both numerator and denominator of the fraction by what you have in the numerator. Okay, for instance, you ask to rationalize 2 over root 3, 2 over root 3 to rationalize 2 over root 3. That gives us 2 over root 3 multiplied by root 3 over root 3. All right, to give 2 root 3 over 3. You have rationalized the sword. All right, eliminating the word, the sword denominator, the sword denominator. That is the essence of what? Rationalization. Okay. We move straight to, okay, there are also other complex tasks to do in rationalizing, all right? Whereby, take notes, if you have an expression 2 over 2 root 5, okay? 2 over 2 root 5. Sorry, 2 over 2 minus root 5. That's the expression 2 over 2 minus root 5. Right? We are to rationalize this expression. We simply multiply the expression by the conjugate of 2 minus root 5. Right? Which gives us what? 2 plus root 5. Used to multiply both denominator and numerator of the fraction 2 plus root 5. Okay, then we express further or further simplify by multiplying. All right, we move on straight to indices, laws of indices. A lot of indices provides us with rules for simplifying calculations or expressions involving powers of the same base. Right on your screen, we see the fundamental laws of indices. Right, 6 of them shown here. We have the multiplication law, we have division law, we have the power of zero law, we have the indices with brackets. All right, we have negative powers of indices, negative powers, and we also have fractional powers. Okay, so starting with multiplying indices, okay, multiplying indices, all right, giving um base A, all right, raised to the power of m, multiplying A raised to the power of n, all right, it gives us A at the single base, then we add up the two powers, m plus n, all right. Secondly, for division law, we have A raised to the power m divided by A raised to the power n, right? That gives us a single base A raised to the power of what? M minus n, m minus n. Okay, so it means when we have same base of an index expression dividing each other, right? We do what we subtract the powers. Same base of an index expression multiplying each other, what do? We add up the power, so it gives us the base raised to the power of the sum of the powers given, right? Now we have the power of zero, okay, knowing that, for instance, a raised to the power zero, you have one, okay, any expression raised to the power zero gives one, all right, note that. Then we also have the indices with bracket, indices with bracket, okay, indices with bracket. So from your screen, you have a raised to the power m, okay, close bracket, then you have raised to the power n, all right. So that gives us what we do is to multiply the two powers in the bracket and the power outside the bracket to give us a raised to the power m n. Okay, now negative power rule, negative power rule. Okay, negative power rule. All right, here we have if a is given by a, or an expression given by a raised to the power minus m, right? That gives us a, sorry, 1 over a raised to the power m, 1 over a raised to the power m. All right, so eliminating the negativity in the power, we introduce 1, right, as the numerator to a raised to the power m, right? These laws are now shown in examples, as shown in your screen. I want to explain. We see multiplying indices. When multiplying indices with the same base, we add the powers. We add the powers. When dividing indices of the same base, we subtract the powers as shown in your screen. Okay, now bracket with indices. When there is a bracket, a power outside the bracket. Okay, what do? We multiply the powers. When there's a power outside the bracket, multiply the powers. Now, any non-zero value raised to the power of 0 is equal to 1. All right, just as I've shown to you. Now, negative indices as well. Yeah, when the index is negative, put it over 1, put it over Okay. Okay, I still like to share my screen. Oh, hmm. Wow. Okay, that was network glitch. Okay, I still go on with from where I stopped. All right. Yeah. Fractional indices. When the index is a fraction, the denominator is the root of the number or letter. Okay, then raise the answer to the power of the numerator. All right. So for instance, you have x, supposedly that's supposed to be a over b, right? Not x a b. X is x is to power a over b. All right. The denominator to that fraction becomes the root of x. All right, becomes the root of x, while the numerator becomes the power to the root of the expression x. Okay, so please take note. Now we can do a lot of calculations with indices. We can do a lot of calculations in this, but whether we are able to apply the rules accordingly, the rules accordingly. All right, there are examples shown to you on the screen. For instance, simplify 4a raised to power 3, multiply 7a raised to power 2, multiply, raised to power 2. Okay, then also multiplying by 4 a raised to power 3, multiplying by 7a raised to power 2. All right, so we can simply expand this by by writing 4 times a times a times a times 7 times a times a times 4. All right, um times a times a times a times 7 times a times a. All right, all these expanded. Okay, all these expanded together. Okay, I think there's a typo error in that example. Okay, so hopefully I see all examples works here would be sent to you, will be sent to you, all right, for clarity, will be sent to you for clarity. All right, so the platform doesn't support some of the notations in arithmetic. There's no platform, so we have to just make do with what we have. Now we see dividing indices, dividing indices. Okay, we have tasks to do in division of indices. Okay, brackets with indices. I've been seeing all that. I've been seeing all that. Okay, so we also see more examples shown to you on the screen. Example 2, right, shown to you coefficient inside bracket. Coefficient, I think I did mention something about that. Coefficient inside bracket. Simplify and leave your answer in index form. A 10 a raised to power 3, close bracket raised to power 2. 10 a raised to power 3, close bracket raised to power 2. So what we'll simply do is multiply the powers, which are 3 times 2, which is 6. So we have 10 a raised to power 6. Simple as that. Okay, so more tasks or examples given on the screen on negative indices. Okay. All right. So power of zero. Okay. Having seen all that. Okay. Fractional indices also touched judiciously. Now, common misconceptions. Okay. Common errors. Now, the multiplication and division laws can only be used for terms with the same base. Note that can be used for terms. You cannot simplify a raised to the power 4 times b raised to the power 3. A raised to the power 4 times b raised to the power 3. You cannot simplify that. That's the best you can go. Okay. Then also, when a power is outside the bracket, you must raise all terms inside the bracket by that power. When a power is inside the bracket, is outside the bracket, right? You must raise all the terms by that power. Now you have, for instance, 4a raised to the power 2. All right, please don't mind the double prints. Okay, that's been causing real confusion. All right, these double prints here, this for example, the one up here, a raised to the power 4 times b raised to the power 3, that's just what you have. Don't mind it's double printing. All right, it's the format. So we have 4 a raised to the power 2. That's what we have in this example. All right, so when you have a bracket outside or a power outside the bracket, that power affects the two terms inside the bracket. So we have 4 raised to the power 2 multiplying a raised to the power 2. That gives us 16 a raised to the power 2. 16 a raised to the power 2. Okay, now I also put here confusing integer and fractional powers. Confusing integer and fractional powers. So a raised to the power 2 equals to a times a. As simple as that. Right? Please don't mind the double prints side by side. A raised to the power 2 is simply what? A multiplied by a. Right? A raised to the power 3 is simply a multiply a. Right? So we also see other misconceptions confusing positive and negative powers. We can have decimal, fractional, negative or positive integers. Okay. Now we also have indices, powers or exponents. Indices, power or exponents. Indices can also be called powers or exponents. Okay. Yeah, I trust and other there's still a lot on this course, on this course, and we hope, okay, for quadratic, I'd like you to go through logarithm, okay, logarithm slash exponential function. We also have quadratic equations, equations of lines and circles. Okay, I can talk briefly on quadratic. Quadratic, an expression is said to be quadratic if the the variable in that expression has the highest power of 2. If the variable in that expression has the highest power of 2. Okay, so note that we have problems of quadratic expressions where we study on how to factorize these expressions, okay, and we apply them to applying operations of factorization of quadratic expression to solve quadratic equations, right? Understanding roots of a quadratic equation, all right? Understanding roots of codification and all that. So equation of lines, AP and GP mapping, permutation and combination, polynomial, trigonometry, differential calculus, and integration. These are other topics. These are other topics in this course. I like you to look up in your library period. I like to call this a close so that I can be able to upload conveniently. Thank you. All the best.